Welcome to today's webinar. Plate and shell buckling utilizing Dlubal Software is the topic today. My name is Andreas Hörold. I am responsible for marketing and public relations in the Dlubal Software company. For instance, the Dlubal website, press releases, customer projects, the German and English webinars, etc. I will be the presenter today. My colleague Sonja von Bloh and Thomas Günther will support me. They will answer your questions. You can ask questions via the control panel on the right side of your screen. You can show or hide the control panel with that arrow here. And then you can enter the question here. Yeah, Thomas and Sonja will answer you. If you don't get an answer during the webinar, because there are too many, you will get an email after the webinar. The other way is to watch the entire webinar and then email your question to info@dlubal.com. I switch off the camera, the webcam. Okay, then you can see the full screen. To the content today, the first part of the webinar is an example about plate buckling design according to EN 1993-15 in plate buckling. And the second part with another example is shell buckling design utilizing the global M&A and LBA calculation according to EN 1993-16 with RFEM. First part, plate buckling analysis of steel plates according to Eurocode 3, part 5. There are three methods implemented. The first is method of effective cross sections according to section 427. The second method is the reduced stress method according to section 10, and the analysis using finite element method according to Annex C. Today we look at an example using the reduced stress method, which is implemented in plate buckling. And that's the example. A panel with the dimensions 500 by 175 centimeters, trapezoidal stiffener in the middle of the plate or panel. Material is steel S355 and the thickness of the plate is 14 millimeters, and there are compression stresses and shear forces. Sigma is 23 kilonewton per square meters and tau 1 kilonewton per square meters. Square centimeters, sorry. Okay, we go to RStab and create a new file. Example plate buckling. Okay. And after I've created the new model, I can open plate buckling as standalone program, plate buckling, or as add-on module, design steel plate buckling. In this webinar, I open this as add-on module. That would be the same procedure if I started from RFEM. Because there is one button for taking over stresses, and I would like to show you that in the add-on module, and that's why I opened the add-on module, plate buckling. That's the first dialog, Eurocode 3, part 5, and you can select one of the national annexes. I leave the standard annex of the European Union. Steel S355, that's correct. And the plate dimensions are 500 by 175 centimeters, and the thickness of the plate is 14 millimeters. That's all for this dialog. Then we need to create the stiffener. It's possible to create transverse stiffeners or longitudinal stiffeners. In our example, we have got only one longitudinal stiffener. In the middle of the plate, from the beginning to the end of the plate. Then here we can select the stiffener type, for example, flat plate. You need to enter the height and the thickness and the position and the arrangement. I select the trapezoidal stiffener with the following dimensions. Height is 300, then the is 150, the width is 200, and the thickness 6 millimeters. Position, that's in the middle of the panel, and the arrangement is on the right side. Okay, we can check that with that button here, graphics, where are the dimensions and the trapezoidal stiffener in the middle. Okay, that's all for this dialog. Next dialog are the loads. I use design loads and the normal stresses, 23 and 23 kilonewton per square centimeters, and 1 is tau. Okay, yeah, and that's the button I mentioned before. If you have created a RSTAB or RFEM model with loads, you can take over stresses from members, from RSTAB or RFEM. The pressure must be entered with positive values, but you can check if you did it right here with that button. You can see the loads also with the graphic button. You can see the dimensions, loads, and the stiffener. Okay, the model is complete. We only need to modify the detail settings. We can leave almost all in the default setting, but I would like to calculate more buckling modes. Okay, and then we can calculate all. So now the program calculates 20 buckling modes, and the first buckling mode, there's an overloading. The design ratio is 105%, but as you can see in the graphic, it's a buckling mode for a single panel, not for the total panel. Let's take a look at the graphics. I select here not only the sigma x or the tau, but the simultaneous occurrence. Okay. So that's eigenmode number 1, buckling shape of a single panel. 2 is the same, single panel. So all buckling modes for single panels. but the 17th eigenmode or buckling shape is a buckling shape for the total panel. And that's why we can use that for our design. So I leave the dialog. I select here design by eigenvalues and scroll down to the 17th eigenvalue, and you can see the design ratio is 76%. And that can be used for the design of the total panel. But then we need to design the single panel as well. So let's do that. I rename the case total panel. Okay. And I create a new case, single panel. Same settings, but the panel dimensions are not the same. 500 by 72.5. Thickness is the same. So next dialog, no stiffener. Same stresses, we have got only compression. So I call it also design loads. Okay. Now then we can calculate the single panel. Okay, design ratio also 90%, and the whole panel is designed. If the stiffener is prone to buckling, a plate buckling analysis must be performed also for the stiffener. The procedure is the same like for the single panel design that I showed here. But I switch to the total panel. Now sometimes it's quite difficult to see what's the buckling mode for the total panel, and as an alternative it's possible to design the total buckling panel by using the analytical calculation method for determining the critical plate buckling stress described in Annex A. The requirements are met. We have longitudinal stiffener in the buckling panel's compression zone, and that's why I copied the case Annex A. Okay, we can leave all as it is. We copied all stiffener, design loads, but we need to modify the detail settings. I need only one buckling mode, but I select here according to Annex A. Okay. And I calculate all. Okay, the design is fulfilled. We have got a design ratio of 93%. For the case A, we got a design ratio of 76%. But in that case, the alternative design for the total panel would be also okay. That's all to the plate buckling. I turn back to the PowerPoint and we come to the second part of today's webinar, the plate buckling analysis of steel shell structures according to Eurocode 3, part 6, where are also 3 methods integrated. First, the stress-based plate buckling analysis. It's a simple application for expert engineers. There are low requirements for computer technology. Often the calculation is done by hand formulas, but economic results are difficult to achieve for load situations significantly differing from conventional buckling shapes. The second method is the plate buckling design by global numerical M&A LBA analysis. There's more background knowledge for shell stability required, and there are also higher requirements for the computer technology. It must be possible to do a materially nonlinear analysis and a linear elastic bifurcation analysis in the program. And computer technology using FE analysis is consequently applied. And the third method is plate buckling design by global numerical GMNE IA analysis. There's excellent background knowledge necessary. You need to apply the correct imperfections, and it's not too easy. Considerable requirements for computer technology and difficult application in real design situations. In today's webinar, we use the method in the middle. That's the example. It's from a report from Professor Schmidt. That's the system here. A simple silo with wall thicknesses of 10 millimeters, 8 and 6 millimeters. The load is a accidental loading. QD is 8 kilonewton per square meters. It's the difference between the outer and inner loads. We enter only the silo walls, including boundary conditions for shells according to table 5.1. Okay, let's take a look at the next slide. We start here with the analysis. At first, the elastic critical buckling resistance ratio must be calculated, RRCR. We do that by an eigenvalue analysis in RFEM. Then we see equation 8.24. If it is not possible to do an M&A calculation, it's allowed to derive the plastic reference resistance from a linear shell analysis. That's the text from the code. In simple words, you must apply this equation 3 times on 3 different places where the maximum values of nx, n theta and nx theta are, and the lowest value, that's the value you use for the design. Sounds quite complicated, but we do that this way. I don't do that this way anyway. We use the materially nonlinear analysis in RFEM. Before we go to the other equations, I start with RFEM. I enter the silo circle via center and radius. Radius is 5 meters. Okay, and then I copy that circle 1 times in minus 3.5 meters. And here I added the expanded settings. I would like to create a new surface between the selected and the copied line. Okay, then the surface is created. I only need to adjust the settings here. Standard. Steel is correct, S235, but the thickness must be 10 millimeters. Okay, copy the line again. Edit the settings here, 8 millimeters. Again, the same procedure, 2.2 meters and 0.8 meters. Okay, I select this one and this one, standard, and 6 millimeters. Okay, in the display navigator, I can show the colors in graphics according to surface thickness. And you can see 6 millimeters, 8 millimeters, and 10 millimeters. That's okay. We only need to define the line supports. We start with the line support at the bottom, local line axis system. We support in all 3 directions. Okay, and on the top of the silo, we support in X direction, Y direction, but not in Z direction. Okay, that's all. The model is complete. We only need to apply the loads. We've got only one load case. I call it design loads. Without self-rate, that I get the same results or similar results as in the report of Professor Schmidt. Okay. In Z direction, that's the axis of the surface, uniform, and 8 kilonewton per square meters. Okay. So, and a linear in Z load. The value 8 is here, and the value 0 is on the top. Okay. That's the triangular load. So now all is complete. The model, the loads, and we can do or run the eigenvalue analysis. We open the add-on module of stability. Now we can leave our settings as they are and calculate at the first 4 eigenvalues in that case. That's the default setting, but we need only the lowest eigenvalue. Here you can see the eigenvalues, and we need that value here. 1.507. I turn back to the PowerPoint. Here you can see the value. Yeah, in this webinar I would like to show you the most difficult parts of the analysis, the determining of the RCR and the RRPL. That's the next step. Okay. That's the mode shape graphically. I save it and then I copy the model because we need to define another model. Out results. Call it plastic. Yeah, we need to define another model because that's another model because I changed the material settings. That's why we can't do that in the same model as the two calculations. Now I deleted first the stability data and change here the material settings. I select the isotropic plastic 2D, 3D. Yeah, you all know the stress-strain diagram with the elastic behavior and the plastic behavior of the steel. Okay. For this material model, the RFMAT-NL add-on module is required. It's important information. So what we do now, we change the calculation parameters here at the top, on the top. For the load case, yeah, if you have got load combinations, etc., you must do the entries for the load combination. Must be a geometrically linear analysis, and I select here the incrementally increasing loading. Initial load factor. Now we need to start with 1. If we don't know what's the expected initial load factor, load factor increment 0.1 and refinement of the last load increment 10. That's are good values to get an exact value. You can also define a stopping condition, for example, 300 or 500 millimeters. That's the value when you expect the model collapses. We don't do that, but we select here, save the results of the load increments. I would like to show you the calculation diagram afterwards. Yeah, the calculation would take several minutes. I skip the calculation time and turn to an already calculated model. In the table at the bottom, here by table 4 results, you can see here the critical load factor. 35.6, and that's the value that is necessary for our design. Here you can see the different increments. Let's start with 35.3 and then I go to 35.4. You can see a quite small deformation. Also in the next step, 30 5.5, also a small deformation, and in the next step 35.6, you can see a quite large deformation in a very small step, and yeah, that's the point when the program stops the calculation. I would like to show you the calculation diagram and the calculation parameters here. This dialog. You can see the increments, increasing the load, and there are quite small deformations, and at that point here the deformation is increasing by very small steps, and that's the point when the program stops. You can also print that diagram in the printout report. Okay, that's our value, 35.6. We turn back to the PowerPoint slide. That's the value, and when you got both values, you can calculate the overall relative slenderness. I have written down the equations here from the code. Lambda cross OV means overall, the whole structure. 4.86 is the value. Then the circumferential elastic imperfection reduction factor according to table D.5. It's only valid for circumferential buckling. To take over this value here. For other buckling modes, that's another equation, but it's in the code. I show you another example on our website. There is the alpha calculated with an equation. Then the plastic range factor, beta 0.6. Plastic limit relative slenderness, lambda cross P. It's smaller than 4.86. We've got pure elastic plate buckling. Some hint, you can download these PowerPoint slides, also the models from our website after the webinar. At the end of the webinar, I show you how to do that or how to find that. Then, because it's pure elastic plate buckling, we must calculate the buckling reduction factor according to equation 8.15. She is 0.0318, and the last steps are the determining of the characteristic buckling resistance ratio, are key, and then the design buckling resistance ratio, RRD. It's 1.03, and the design is fulfilled. Here's the link to another example on our website. In that example, there's pressure or a load at the top of the silo, and that's why there's meridian pressure buckling, and the alpha is calculated by this formula, and that's the same workflow here that I showed in the PowerPoint slides. Okay, now I think that's not too difficult to apply these equations. The most difficult part is the determining of RRCR and RRPL, but that's what I showed you in this webinar. Okay, that's the end of the part 2. That's the bibliography. You record the parts and the report of Professor Schmidt. At the end, I would like to introduce you the free online services on our website. Please use that. For example, our GeoZone tool with the snow, wind and seismic zone maps. You can quickly find out what the correct values are for the special place. The cross-section properties, you can also define parameterized cross-sections and find also data of cross-sections from an extensive section library. Then the FAQ and knowledge base with a lot of valuable articles. The models to download, there are about 1,000 models on our website that you can use for exercises or for your projects, etc. Then the YouTube channel with the free webinars and the videos. Our web shop is with prizes. You can download the trial licenses of, for example, RFEM and RStab with all add-on modules. The standalone programs, plate buckling, for example, and shape fin, craneway, our wind simulation, etc. If you haven't already registered for our newsletters, just register on our website and then you get information about upcoming webinars, videos, online trainings, or news about our software. I would like to show you how to find that's our homepage, the slides, etc., news and events, webinars. In the next days you will get a link with that leads to that page here, and then you will find the recording here on that place. Before the webinar I already downloaded or uploaded the presentation slides here and the model files. Also here you can see already the silo. Okay, then we are at the end of the webinar. I switch off on the webcam again. Thank you for your attention. Thanks to my two colleagues for answering the questions. When you close or leave the webinar, there's a small survey. Would be very nice when you fill out or answer the short questions. It's quite important for our quality management. Please note that the worst score is 1 and the best score is 5. Maybe we can see or hear each other in another webinar. I wish you a nice rest of the day and bye-bye.